I have the great pleasure to welcome our second invited speaker of the day. It's Eleanor Rieffel from the NASA Ames Research Center, and she's going to be talking to us about the use of NISQ devices to evaluate quantum algorithms. Thank you for joining us, Eleanor. Please, the floor is yours.
Thanks. I seem to be having some problems with the slides. Can you still see them?
Looks good to me.
Can you still see the slides?
Yes, I can see the slides.
Great. Okay. Thank you for the invitation. I would like to talk broadly about utilizing NISQ devices for evaluating quantum algorithms. A lot of the work is done in conjunction with the wonderful team here at NASA Ames and our many collaborators, and we'll also mention other work. So let me dive in. One thing we frequently get asked is, why is NASA interested in quantum computing? And if you think about it, NASA is just constantly confronted with massively challenging computational problems, from its space exploration missions to its aeronautics missions to its earth science missions, et cetera. For that reason, NASA has long had one of the fastest supercomputers in the world. And back in 2012, NASA decided to start a quantum computing group to determine the potential for quantum computing to enable more ambitious and safer NASA missions for the future. So that's what the group looks at, and that fits well with our current interest in NISQ devices as a field, as well as longer fault-tolerant devices out in the longer term. NASA has quite a long-term vision. That's how it can do such ambitious missions. So I just wanted to give you a sense for where we're coming from. As most of you know, quantum computing has entered the NISQ era. Quantum supremacy has been achieved. We're able to perform computations in a few seconds that aren't possible in even close to that time on even the largest supercomputers. And that is extremely exciting, but no one has yet demonstrated useful quantum supremacy. And the processors are currently just too small and too noisy to be useful for solving practical problems, with the possible exception of, if you happen to be interested in certified random number generation, that may be an early application. But in general, applications will require larger and more capable devices. So what should we do with these very exciting but still limited quantum devices? So there are a couple answers to this that, and I will emphasize the algorithmic investigations in this talk, but there is a real feedback loop between insights gained into next generation algorithms and next generation quantum hardware. So we're now in a new era where quantum heuristics can come to the fore, in that we can now perform computations not possible even on the largest supercomputers. And that allows us to explore and evaluate algorithms that can be only explored via experimentation with the hardware, because there's a generic exponential slowdown to simulating on a classical computer. So there are two classes of processors. They're general purpose universal quantum processors that can run any algorithm, but require very specific control, whereas there's also special purpose quantum processors that may be tailored to one particular algorithm or one particular application, with the most prominent one currently being quantum annealers. So I will talk about both of these going forward. To start off, however, I want to just mention the status of quantum algorithms. As everybody knows, there have been a number of very, very exciting quantum algorithms, starting with Shor's algorithm back in the mid-1990s, with a provable advantage over the best known classical algorithms, sometimes with stronger guarantees according to standard classical complexity conjectures. We also, on the other hand, know some limitations on quantum computing. So for example, Grover's algorithm for unstructured search, that's the best you can do. And in between, for most applications, we don't know what the quantum advantage will be. And this is not surprising because even for classical computation, provable bounds are very hard to obtain. And analysis is just too difficult for many practical classes of algorithms that are very computationally challenging. And that's why there are, for example, SAT competitions, machine learning competitions, planning and scheduling competitions, et cetera, where people run on standard benchmark sets of problems and see how these approaches work. And the field improves from year to year as people work on these algorithms, and also use them for practical applications as best they can currently. And until quantum hardware reaches the point where it can run where classical algorithms, classical simulation cannot keep up. Emerging quantum hardware enables us to test quantum algorithms that otherwise we haven't been able to explore in this empirical way. This empirical exploration will enable a broadening of applications of quantum computing significantly beyond what we see. The argument here is that we've been able to actually prove bounds in a number of cases. And classically, most cases for really tough computation, we can't prove bounds. So what's the chance that for quantum computation, those are the only cases where you can see quantum speed up? It seems much more likely that as we explore things empirically, we will see a lot of improvement via quantum heuristics. So one possible target for this heuristic exploration is optimization and sampling. There are instances of combinatorial optimization problems that are frequently solved by classical heuristics, and also for machine learning. And there are a number of quantum algorithms that have been suggested. I'll particularly look at ones that we can explore in the nearer term, such as quantum annealing, adiabatic quantum optimization, and QAOA. And I want to emphasize at this point that there are diverse optimization goals. So you may be looking for exact optimization with guarantees that you've actually found the exact optimum, or you may want approximate optimization with guarantees where you know you're within a certain ratio of the optimum. You may be okay with just a good heuristic where you don't have actual guarantees, but you've been able to see empirically that it generally performs pretty well. There are also other optimization goals, like you may want to sample from a variety of exact or approximate solutions to your problem. For example, having a portfolio of solutions where when certain uncertainties are known, you can choose between them, just as an example. And there are also sampling goals for machine learning. So for example, you may want to sample the thermal distribution corresponding to the cost function. Sampling from a Boltzmann distribution is common for the classical techniques. So I'll continue on looking particularly at these three optimization algorithms. So common elements across these algorithms are that you have a classical cost function that leads to an operator that includes penalty terms to enforce constraints. You also have some sort of driver or mixing operator that helps to explore the search space. This is most frequently the transverse field, just the sum of the poly X operators, though we will shortly see other mixers. So in adiabatic quantum optimization, you evolve under this Hamiltonian that's a combination of the problem Hamiltonian based on the cost function and the driver Hamiltonian based on the mixer. And the idea here is to go slowly enough that you stay in the ground space. However, since the goal of the quantum computing is to do something quickly, and also it's hard for hardware to really stay in the adiabatic regime for the harder problems, what we've looked at a lot is something very related, which is quantum annealing, which has many quick runs of the same Hamiltonian. And here also it's an open system with thermal effects contributing potentially to relax back down into the ground state after excitation. And well, also more recently, QAOA has been investigated heavily. It's an alternation between these two phase separation operators based on the cost function and mixing operators for a certain number of iterations. And I'll now go into a little more detail on that and then loop back to some quantum annealing work later and then get into some of the tools for these. So one of the things we've done is extend what was originally the quantum approximate optimization algorithm to an Ansatz, the quantum alternating operator Ansatz. So the quantum approximate optimization algorithm is a gate model algorithm due to fore and co-authors, and their aim was to come up with an approximate optimization algorithm with guarantees. And the form of that iterates between two Hamiltonians p times, the phase separation, which is cost function dependent, and a mixer. And early results showed that as p goes to infinity, it converges to an optimum, which is good. The proof there is basically trotterization of adiabatic quantum optimization. So that's already a connection between these. They were able to show also that in a separate work, that for p equals 1, proofs from IQP circuits could be modified to take to work in the QAOA setting. And so it's provably hard to sample from these circuits, very, very simple circuits, up to standard complexity theory conjectures, and also briefly beat the existing classical approximation ratio on max E3 Lin 2, only to inspire better classical algorithms. So that was exciting. But for example, the sampling result here shows that this framework of alternating between these two operators is interesting for exact optimization and sampling, as well as for the original goal of approximate optimization, and also may be useful as a heuristic rather than where you have an actual guarantee on the approximation ratio. We also showed that within the QAOA framework, there's an algorithm for Grover's unstructured search, which achieves the root n query complexity, and that is one of the few large P results for QAOA at present. So we generalized this framework of alternating between a mixer and a phase separator. And the advantages of the framework that I'll describe going forward is that it supports more general mixing operators. And these were inspired by our look at how one compiles these things to actual hardware to try to run in the near term. It also incorporates hard constraints into the mixer instead of as a penalty term in the cost function, which is how it's generally been done in quantum annealing. Because in quantum annealing, for the quantum annealers so far, one's restricted to being able to program the cost function based term and not change the mixer, though hopefully that will change going forward. So the QAOA, the Ansatz here allows a more efficient search because it explores only the feasible subspace, which is often exponentially smaller, but still exponentially large. And we've mapped many problems to this extended QAOA formalism, and I'll show you some results. So let me just review basic QAOA circuits. So a level P QAOA circuit has the following form. You start with an initial state. In the most common case, this is just a Hadamard applied to all qubits. You loop P times, applying a phase separator and a mixer, and then you measure in the computational basis and you obtain a bit string. And you have circuit parameters here, the betas for the mixer and the gammas for the phase separator. And you can show that under certain constraints, certain assumptions, that the bit string returned is within a good approximation ratio with high probability. And in more general, it may just be a good heuristic. And it's important that the goal of the algorithm is to return a good bit string, not necessarily to estimate the expected value, but because the estimation of the expected value is often much simpler, people often estimate the expected value and then once to determine the parameters, and once they have some good parameters, they will then run the full circuit to obtain the bit string, the desired bit strings. So that's QAOA in a nutshell. And now I'll go on to, oh, and I should mention that, so for the parameter setting here, in the original QAOA paper, they were able to show that under reasonable restrictions on the cost function, there's a polynomial time classical algorithm for constant P, but as P grows, this grows exponentially. So approaches to parameter setting include determining good parameters analytically. For example, that was done in the Grover unstructured search approach that we mentioned above. And it also allows you to determine good parameters via classical algorithm in certain cases, or by running small decomposed parts and piecing them together and updating the parameters. There are a number of approaches here. So let me continue on to the quantum alternating operator Ansatz generalization. So what's important here is that we're still alternating between the phase separator and a mixer, but we've generalized the mixer so that instead of being just e to the I beta k at round k of a single Hamiltonian h, it's the product of a bunch of Hamiltonians. You still have just the one parameter bk, but you have a number of Hamiltonians here. And you should think of this as, for example, the h's corresponding to your single and 2 qubit gates that you can actually implement on the hardware. And if you have a global Hamiltonian of the form e to the I hj, which involves all the qubits, if there are terms in the Hamiltonian that don't commute, then implementing it well on the actual hardware is hard, because you're going to have to do something like tritorization and break it down, and then you get many, many gates, and you quickly run out of your decoherence, run into your decoherence limits on the hardware. But there's no real reason why the mixer needs to be of that form. So from our look at compilation, we can come up with some design criteria for these mixer operators and have them be in terms of small numbers of, or smaller numbers of single qubit and 2 qubit gates, or whatever's implemented on the hardware. So that's the general idea. I'll go on to walk through the max K colorable subgraph. So given a graph with vertices V and E and K colors, we want to find a color assignment that maximizes the number of properly colored edges, where a properly colored edge means the endpoint vertices have been assigned different colors. We're going to use, there are other possibilities, but we're going to use a one-hot encoding where there are NK variables, where each variable corresponds to a vertex and a color, and it's 1 if that vertex is colored. So XUJ is 1 if vertex U is colored color J. And we can write the cost function as the number of vertices minus the miscolored edges. But in this encoding, we must avoid invalid colorings where a vertex is labeled either with 2 colors or no coloring at all. If you allowed no coloring at all, a very easy way to optimize this is not to color anything. So this constraint is very, very important. And you'll notice that for each vertex, what you have is constraint that it be in the Hamming weight 1 subspace. So we could add that constraint to the cost function to enforce penalties, as is done in quantum annealing, but it's better to design a mixer that keeps the evolution in the feasible subspace. The initial state choice, therefore, is very important. It needs to be a feasible state. It doesn't have to be a very good state. So for example, for this max K colorable subgraph problem, we can start with all colored red. That's easily implemented, but is very far from a good state in terms of the colorability. But it does have 1 color per vertex. One could also start with a superposition of feasible states, for example, the superposition of all colors, the W state on each vertex. And as a mixer, we're going to use a swap or XY mixer rather than the bit flip mixer. And the reason for this is that this allows us to preserve the Hamming weight. So And there are a few different versions of this. You can have a ring mixer where you've ordered the colors and you apply swaps to adjacent colors only. So if blue and red are adjacent, this mixer swaps. If you're colored red initially, it swaps so that you're colored blue, etc. You could also have a complete mixer where there's a swap between each of the pairs of colors. There are some possibilities in between with next nearest neighbors or the like. Complete mixers mix more quickly, but have a higher circuit depth. So you may want to make a choice here when compiled to realistic hardware. You also have a choice of how you partition these. So notice that these XX plus YY operators do not commute with each other when they overlap in qubits. So you may want to partition your mixer. So for example, for your ring mixer, you can partition so that you do all of the swaps starting with an odd color at once, and then starting with all of the even ones. And there's, if K is odd, you need to take care of that one last odd fellow. But anyway, you can partition this into this product of these swap operators that do commute because they are on different qubits, and have this done in 2 steps. So that's an example of the generalized mixer where you have these 2 Hamiltonians, but still 1 parameter beta K at each level K. So we have numerical results showing the advantage of the XY mixer, which confirmed the intuition that because the feasible subspace is so much smaller, you should get an advantage. And it's worth noting that this ratio shrinks with n, so you should get more and more of an advantage as the number of colors increases. We've also looked at the ring versus the complete mixer, and not surprisingly, the complete mixer mixes more quickly. But as I said, there's a trade-off in terms of implementability. And there's also a trade-off in terms of the choice of initial states that affects performance. Again, not surprisingly, the W state is a better place to start than the single classical state, where all things equal, but they're not equal. The W state, it takes a much greater depth circuit to implement, and so there's some trade-offs here. So when you're actually confronted with running these things on actual hardware, there are some decisions to make based on what you have available. I'll also mention that we have results that should be coming out next week on this under noise, and showing that you still have that the XY QAOA still gives a big advantage for these even under noise, but certainly error mitigation techniques are needed, as is generally the case for things we're running on NISQ devices. So with that, I'll just mention that there's been a lot of work on parameter setting for QAOA, and there are some discouraging results about the parameter setting getting stuck. And most people worry about the parameters getting stuck in local minima, but actually a huge problem is the parameters ending up in a large featureless plateau with no indication as to what direction to go, and so can just wander aimlessly there without getting any improvement at all. So that's this barren plateau paper. On the other hand, as we mentioned, for Grover's unstructured search, a simple periodic set of parameters recovered the square root query complexity. I just want to note that this is not a trotterization of the Roland-Surf adiabatic algorithm, since trotterization would lose the square root query complexity because you have to alternate too quickly in the realm of the minimum gap. So this really is a novel algorithm here. But it's encouraging that one could find a simple set of parameters for this large P case. On the other hand, for the trivial problem of a max cut on the ring, good parameters are harder to find than one might expect. Fermionic view helps with the analysis. We looked at that in the paper down at the right, and more recently, Mbang, Fazio, and Santoro have advanced these results, though there are still some open questions, even just for this very simple problem of max cut on the ring. Ross, could you let me know what my timing is?
You are at half past.
Okay, great, thank you. There have also been recent connections between quantum annealing schedules and QAOA parameter setting. So, for example, the first reference here identified regular subfamilies of optimal parameters that resemble digitized smooth evolution. Very interesting that for easy problems, it resembled an adiabatic schedule where throughout the circuit, it stays close to the ground state. But for harder problems, it resembled a diabatic schedule where it does not stay near the ground state of the the Hamiltonian that it's digitizing mid-anneal. The second reference here showed that Pontryagin's minimization principle implies optimal evolution schedules must be bang-bang, except for in cases with degeneracy. And then the third one showed that generically for a fixed amount of time, the optimal procedure has a bang-bang structure at the beginning and the end, but more like a digitized smooth annealing structure in between. So it's great to see advances in understanding the theory and what would expect here, both positive and negative results. And it's also very exciting to see the connections between QAOA and quantum annealing, because quantum annealers, we can run much larger instances at present, though there are restrictions on the sorts of schedules one can run. While QAOA ramps up, and similarly, insights into QAOA can give us insights into quantum annealing schedules. So confirming, for example, that one really wants to look at diabatic quantum annealing, not just quantum annealing where you are in the adiabatic regime throughout. So, and there's also been advances in obtaining the mean value, the expectation value, which is useful for finding these parameters, at least reasonable parameters, and you would expect that the bit values that you read out will congregate around the expectation value in cases where you have concentration. And so these algorithms that help us obtain the mean value for small p help us with the parameter setting in these cases, though in some cases, these still have a very large constant factor or maybe an improvement, but are still not polynomial time. Depends on the specific cases here. So just wanted to point to that. And I'll now transition over to some work on quantum annealing. So the plot on the left shows a standard quantum annealing schedule with the driver Hamiltonian in blue and the problem Hamiltonian in red. And you start the anneal in the ground state of the blue, the driver Hamiltonian, and you gradually increase the problem Hamiltonian in the hopes of ending up in the ground state of the problem Hamiltonian or close at the end. And a number of people realize that thermalization effects are happening on current quantum annealers, and that there may be an advantage to pausing after the minimum gap, so exciting through the minimum gap, and then pausing to allow the system to relax back down to the ground state. And at first that wasn't the sort of schedule that one could do on a quantum annealer, but D-Wave eventually did implement this, and they did this shortly before Jeff Marshall started his internship with us. He's now a full collaborator, but on the second day of his internship, he got preliminary results looking very much like the heat map on the right. And the diagram, so you'll see that that improves the probability of solution by orders of magnitude if you pause somewhere in the region of 0.4 through the anneal, and that even relatively small pauses give you an improvement. So the diagram down below on the right shows a qualitative picture of what's happening. So for the first part of the anneal, there's large separation between the ground state and the excited state of the anneal. You're close to the driver Hamiltonian. Then you get into a place where the driver Hamiltonian and the problem Hamiltonian are more equally weighted, and the excited state becomes close to the ground state, generally in the, so the minimum gap, it occurs in this area. And so generally you'll see excitations here. And then the problem Hamiltonian increases and the driver Hamiltonian decreases. So the gap increases and you're having less in the way of dynamics. And so in this region, you start to lose the instantaneous thermalization. And so it's in this region that you want to pause and let the system relax. And then for the end of the anneal, you really don't see much dynamics. The dynamics have basically frozen out. So your population in your ground state and your excited state don't change much in that last region. So it's in this pinkish purple region that one would expect that the pause would be useful, and that's what the experimental results saw. Now here we were looking at native problems on the hardware to get these initial results. An interesting question is whether for actual application problems, this can get you a win. So we looked at spanning tree problems with degree bounds. It's the bounded degree that makes the spanning tree problem hard. And we embedded these instances and looked at the ferromagnetic coupling strength between the embeddings and showed that for these problems, for the correct ferromagnetic coupling strength, for a set ferromagnetic coupling strength, we can improve the time to solution as well as the probability of success. You have restrictions on how strong the ferromagnetic coupling strength should be. It also, if it's too strong, it also interferes with the ability to get out of local minima. So there's also a sweet spot there, even apart from hardware issues. So anyway, we found the optimal ferromagnetic couplings, and then within that, we looked at the pause location and the pause time. Note that just increasing the probability of success does not necessarily improve the time to solution, because you're wondering, you have to compare between the longer time that the anneal is taking compared to running many, many times potentially in that. So we want to look at relatively short pause times. So we looked at pause times from 1/4 of a microsecond up to 2, and we were able to show that indeed you get improvements in time to solution for the best values here. So that was exciting. There's still lots of open questions as to what are effective schedules for quantum annealing, and what are good parameters for QAOA. And the answers may be different depending on whether you're looking at exact optimization or approximate optimization, or you're trying to do Boltzmann sampling, or you want to get a sample of good solutions that have a good approximation ratio. So lots of work here, and also trying to understand where to get intuition beyond quantities related to the minimum gap, which is often hard to find. So lots of open questions here. And now I'll move on to some tools. So one of the things we've looked at is qubit routing on NISQ processors. So you want to run an algorithm on a processor. Let's assume it's already decomposed into native gates, but you have restrictions on which qubits can talk to each other. So you need to get the states that you want to apply a gate to on adjacent qubits. For the moment, I'm talking about superconducting qubit architectures. And so you want to do a bunch of swap operators to get the qubits near each other so that you can apply 2 qubit gates. You can do these gates in parallel. So there's an interesting routing problem of moving the qubit states to locations where the required gates can act on them by inserting swaps into a circuit composed of native gates. So we have results on showing that any unordered set of k-qubit gates on distinct k-qubit subsets can be ordered and parallelized in order n to the k-1. So that's the worst case setting. There's applications to QAOA and also to quantum simulation of fermionic systems for this work. And we've also done a lot of qubit routing for compiling to realistic hardware. Qubit routing can be phrased as a temporal planning problem where you're minimizing make span. And the difference between make span and depth is that make span takes into account the possibly varying lengths of time for the different quantum operators as opposed to just the depth of the circuit. So that's important in these early devices. This expressive framework can incorporate a variety of constraints. Our initial experiments focused on max cut, but we have more recent results on graph coloring. We also have more recent results using constraint programming and improved results combining temporal planning with constraint programming. And very recently, we've gone beyond looking at just superconducting qubit architectures to ion trap architectures. And I recommend that you, if you're interested in this, to listen to Kyle Booth's talk tomorrow morning. Well, I guess it's, well, look at the schedule. It's since this is an international conference. The instances we used are available here for anybody to do testing of their various approaches. And I think it's interesting many approaches have looked just at depth. I think it's interesting for people to look at this make span objective as well. So a plug for that. And I just want to end with a historical perspective. Back in 1972, NASA Ames director Hans Mark brought the ILLIAC-4 to NASA Ames. It was the first massively parallel computer. And sometimes I make people guess this, but at the time, and this was the peak, the fastest computer in the world at the time, had a 50 megaflop peak. And this is not a typo. It had 64-bit processors. And so when I first started at NASA Ames, people wondered what these quantum devices were really good for. And they looked pretty hopeless against current supercomputers. And some of the young people in the division were very doubtful. They could run stuff on their laptops that could beat what was currently available in terms of quantum devices. But some of the older folks stopped by and said, we know what you're going through. We were here in the 70s, and we had the challenge of finding good problems and good algorithms that could really show the advantage of parallel computing going forward. So there were a lot of questions at the time as to how broad the applications of massively parallel computing really would be, how quickly this would scale up. Will these computers ever be able to compete, for example, with analog cases like wind tunnels? And I just want to end by saying that if quantum computers can have even a small fraction of the impact of massively parallel classical computing, we will have made a substantial dent in the world and for NASA applications specifically, which is our main interest here. So with that, I'll end and and see if there are any questions.
Thank you very much, Eleanor. That was a lovely talk. I will go to the Slack and see what questions we have. And
Great.
well, while I read out the first one, I hope all of you will ask us some more. The first question is from Peter M. And he asks, are all your quantum annealing algorithms run on the D-Wave machine?
So yes and no. Those are the devices with by far the most qubits, but we are part of the originally IARPA QEO, now DARPA QAFS program, where we work with folks led by the USC team to run things on hardware that's being built there. There's small things in the lab, and we also run things in simulation. And one of the things I didn't touch on, but probably should have, is that we also don't want to fool ourselves. And so one of the areas we have worked on is developing classical heuristics, often inspired by what we're seeing in the quantum annealing work. And we have a set of software tools that we're very pleased to have come up with the name UFO, for Unified Framework for Optimization. And if you're interested in that, please reach out. Salvatore Mandra is the main point of contact for that, but you can reach out to me as well.
Okay, thank you. I think I'll ask a question of my own now. So just to come back to the first half of your talk, you were talking about mixers for QAOA. Yeah. And I was wondering if there was any general rules you were able to abstract about what makes an effective mixer for NISQ devices. I guess. Yeah,
so in our original quantum alternating operator Ansatz paper, we put in some criteria. We believe that those are good minimal set of criteria. So for example, the mixer should have properties so that with iteration of the mixer, you can potentially reach all of the feasible states. So, a bunch of sort of common sense criteria like that. In terms of which of these, in terms of design beyond that are really effective, there's a lot of open questions. And some of those I think can be just dealt with by advancing the theory, but others, it will very much depend on, in some cases, quite picky implementation details of the hardware. As I mentioned, for example, there's trade-offs in the, for example, whether you go for a ring mixer or a complete mixer. If you have all-to-all connectivity, you might as well go for the complete mixer, but if you don't have all-to-all connectivity, then there's some trade-offs here. If you have an easy way of generating W states, you want to do that, but in general, that's a higher depth, and so there's a trade-off. Yeah.
Just keeping on that point, I mean, since you've done the experiments on actual hardware, do you see a big variation in how noise affects the mixers beyond what you would just expect from more depth, or is it kind of indifferent?
So for the XY mixer, it's certainly very much affected by noise, but because you're in a exponentially smaller subspace to begin with, even if you start like a penalty version of the QAOA with an X mixer, even if you started in that feasible subspace, the standard mixer just drops you out of that very, very quickly. With XY QAOA, it drops you out at less of a rate. Now for high P, they're both going to be really bad, but in this, in the realm where you're wanting to do these things on the NISQ devices, the XY has a clear advantage. But we definitely need to still do some error mitigation there. And there's the potential for taking advantage of the symmetries to do somewhat more resource efficient error mitigation. And we have a very first little step towards that in the paper that I mentioned will be coming out next week. So.
Okay, I will take this opportunity to expose my own ignorance here and ask a really basic question, which is, what do you mean by a bang-bang schedule? That was a new term for me.
Oh, I'm sorry. I should have explained that more carefully. So if you have a bunch of terms in your Hamiltonian, so let's take the case where you just have a single cost function Hamiltonian and a single mixer Hamiltonian. Then what Pontryagin's minimization principle says is that at any point, the weight of the Hamiltonian should be either at its maximum or at its minimum. So that gives you very, very far from smooth schedules, it looks like, because you're going for a while with, say, your cost function Hamiltonian at its height, and then all of a sudden you drop down to where it's at its lowest value, like turned off perhaps. Then at some point it hops back up. And so that looked, so that's what's meant by bang bang. You're going back and forth between these things. And at first that seemed about as far from annealing or adiabatic quantum computation as you could imagine, because those tend to be very smooth schedules. But if you look at digitized versions of those schedules where you're doing this sort of bang bang, you can show that, and the references there showed that you can get these sort of digitized versions of the bang bang, of the smooth schedules give you a bang bang schedule. And so there's now a tie between the smooth evolution and the the bang bang results. Was that clear? Should I go back to some of the
No,
slides?
that's clear. That's clear actually. Just as a follow up on that, does it then matter how quickly you flick between the 2 points?
Absolutely.
Right.
And lots of as yet unknown, unanswered questions there. So lots of room for related work here. Yep.
Okay, great. Well, I think we will wrap up at this point. Eleanor, I hope you will be able to stick around and answer some follow-up questions in the Slack channel.
I will. I'll move over to the Slack channel. Yep.
As an advert for later on, if you are interested in all these questions around routing, there is a session tomorrow where I think all the talks are on routing, including the one by Kyle Booth that Eleanor referred to earlier. And with that, I will say cheerio, and I'll see you in the next talk. Ciao.
Thanks, Ross.